Let's continue talking about the Cisco ENCOR topics that we can actually test in a simulation lab. These are the topics that we have covered so far. Let's go now for 2.3.a, which is LISP. We are going to break down this chapter into several sessions in order to keep them short. Remember that after reviewing the theory, we are going to actually go and configure LISP inside our DNS3 lab. In this session, we will see what is LISP, the separation between location and ID, LISP as an overlay protocol, and LISP approach to routing. Okay, how could we define what is LISP? Well, first of all, it stands for Locator ID Separation Protocol. It stresses the difference between locations and IDs. It can also be defined as a control plane overlay protocol. Cisco also defined it as a network architecture. And as we will see later on, LISP offers a different approach to routing. In order to understand how LISP works, we need first to understand what is the difference between locators and IDs. So, LISP establishes separation of network elements within a LISP domain. So let's say that this is our LISP domain. This is a network where we are running LISP as our overlay routing protocol, and we need to identify what are the IDs and what are the locations. So in order to explain this in a simpler manner, just think of the IDs as the local area networks. So this could be an ID. More specifically, LISP call these endpoints IDs, because endpoints IDs can be as large as local area networks or as small as a single user device. So we have this EID A, and we have this EID B, and here we have this EID C, and we have this EID D. Now, after identifying what are our EIDs, we need to identify what are our locations. Think of the locations, in order to explain this in a simple manner, as the routers that are connecting these EIDs to the LISP domain. So for instance, this router 1 is connecting the EID A to the LISP domain. So more specifically, LISP uses the concept of RLOCs. So the RLOC is going to give me the location of these EIDs. So for EID A, we can say that we can have this RLOC that could be the IP address that belongs to this interface connected to R1, or another RLOC for this EID A could be this, the IP address that belongs to this interface connected to R1, or another RLOC for EID A could be the IP address that belongs to this loopback that is connected to router 1. So this could be RLOCs for EID A. In the same manner, if we had this router, let's say router 3, the RLOCs that we have available in order to reach EID C could be the IP address of this interface that is connected to router 3. We could use this other IP address as RLOC, or we could use the IP address that belongs to the loopback interface connected to router 3 in order to reach EIDC. So that is the difference between locations and IDs, or more specifically between RLOCs and endpoints IDs. And here is where things start to get interesting with LISP, because LISP establishes that we can separate the addressing domains when referring to IDs and when referring to locations. So for instance, I could use IPv4 IP addresses in order to provide addressing to IDs, And at the same time, I could use IPv6 addresses in order to provide addressing for locations. So let's compare that to what we are used to do with traditional IP protocols. Most IP routing protocols uses the same addressing for both the next hop and the destination. So for instance, if this router wanted to reach this destination, it should go through the next hop. Notice that the next hop is an IPv4 address and the destination is also an IPv4 address. If we wanted to do something like this, that will be impossible with traditional IP routing protocols. If I wanted to reach an IPv4 address through an IPv6 address, that cannot be done using normal routing protocols. So thanks to this specific separation of location addressing and ID addressing, we may use different protocols. So with LISP, it's perfectly possible to reach an ID that has an IPv4 address through an RLOC that is actually an IPv6 address. We can also define LISP as an overlay protocol. LISP actually requires another protocol in order to work that we are going to call the underlay protocol, and it needs this because all the routers that comprise the LISP domain needs to share their IP addresses, these interconnection IP addresses, the IP addresses that belongs to their interfaces and loopbacks needs to be advertised. And we are only going to be able to advertise these IP addresses through traditional IP routing protocol. So for instance, we could use OSPF. So OSPF becomes, in this example, the underlay protocol, whereas LISP become the overlay routing protocol. Remember that LISP needs this information because these IP addresses are going to become the RLOCs in order to make LISP work. Now, what we have explained so far is LISP in the traditional manner, in the way that it was conceived originally, that is, it was created for carrier networks, for wide area networks. However, Cisco has chosen LISP for its fabric solution for the enterprise. In these fabric solutions for the enterprise, the overlay is split in two parts. So we have the overlay that is the control plane, and we have another part of the overlay that is the data plane. So for Cisco, the solution is using LISP as the control plane and VXLAN as the data plane. If you don't want to use Cisco, you can use a multi-vendor approach. In that case, you could choose EVPN as the control plane and VXLAN as the data plane if you want. Now, the other advantage of using LISP is that it can create tunnels on the fly. So for instance, if a device here wanted to communicate with a device here, LISP has the capability to create a tunnel with a new IP header plus the LISP header in order to transport this traffic over the network. It will create a tunnel automatically on the fly for this particular communication. And this has several advantages. For instance, if we are able to create tunnels, we can also create or manage BRFs. LISP can also be defined as a network architecture. When defining our LISP domain, we are going to assign roles to these devices. So for instance, if we have a device that is more robust than the others, it has more memory, it has more CPU capacities, we can select that device to store all the routing data for the LISP network. For instance, this device. Devices that connect endpoint IDs to the network perform another role. So for instance, this router, and this router connect endpoints IDs to the LISP domain. So they have a specific role. And devices that connect the LISP domain to non-LISP networks have another role. So for instance, this device that is connecting the LISP domain to a non-LISP part of the network, for instance, the internet, or just another part of the network that is not running LISP, performs a particular role. Perhaps the most interesting feature that LISP has is its new approach to routing. With traditional routing protocols, all routers must know paths to all known destinations at all times. So for instance, in these examples, router 0 is connected to router 1, 2, and 3. And if we were running a traditional IP protocol, router 0 will build its routing table like this. It will know that this destination is reachable through this next hop, this destination is reachable through this next hop, and this destination is reachable through this next hop. Now, what if the only traffic that this router 0 is moving is from this device to this server, from this device to this server, and from this device to this server? It doesn't make sense to have such a big routing table if the only traffic that router 0 is moving is towards this particular server. So what LISP establishes is that there is no need to know paths for all destinations if not all destinations are being used in order to move traffic toward them. So LISP works similarly to how our computers or end user devices use DNS servers. When your end device wants to open a particular application, it will ask the DNS server for the IP address of this particular application. So we don't need to have the IP addresses for all applications stored in our end user devices. We can go and ask a DNS server what is the actual IP address where this application lives. In the same manner, with LISP, routers do not need to have a complete routing table. As they need to move traffic, they will ask a central device what is the RLOC for particular destination endpoint IDs. So with LISP, routers reduce their effort to constantly updating a large routing information base that contains destinations that the router is actually not moving traffic to. So what LISP routers do is actually have a cache where they will store this RLOC to EID information that they just received from this central device. So in this example, as this client wants to send traffic to this server, this particular router 0 will ask this central device for the RLOC for this destination. The central device will inform router 0 that the RLOC for this particular destination or EID is this RLOC. So router 0 will store this information in the cache. So for this EID, the RLOC is this. So the effort for this router is reduced. It has no longer to keep updating its routing information base for all the destination in the network. It only requires to have this cache where it will store the RLOC that belongs to a particular EID to what this router is moving traffic to. So this is the summary of what we saw in this session. The separation between locations and RD, we saw that these are actually known as RLOCs and these are actually known as endpoint IDs. We can use different addressing for EIDs and for RLOCs. So for instance, we can have IPv4 IP addresses for RLOCs and IPv6 addresses for EIDs. We need an underlay protocol to help LISP as an overlay protocol in order to know the RLOCs of the network. LISP follows a network architecture where devices play different roles. There is a central device that knows all the routing information for LISP. There are devices that connect EIDs to the LISP domain. There are devices that connect the LISP domain to outside networks that are not running LISP. And we saw the LISP approach to routing, where we explained that routers using LISP no longer need to maintain a large routing table for all destinations within the LISP domain. They only need to know particular RLOCs to destinations to which the router is actually moving traffic to.